Something I'm not sure that I touched on as well as I would have liked to have when talking about what an exponential function is and what it represents is like maybe a good illustration. So I think I talked a lot but didn't maybe show you guys in a way that's useful. So I say in the video that bacteria population is pretty classic exponential. So, or you can think of like cells, right? So you start with one cell, it divides into two cells. Each one of those cells divides into two. Each one of those cells divides into two. So the more you have, the faster it grows, right? So one, this is a difference times two times two times two, but this isn't like just something squared, right? This is always 2 to some new power. So this is exactly how an exponential function behaves. The more you have, the faster you grow. And this is exactly why the COVID-19 is spreading like it is and why it's so important to do the social distancing. One person, you know, even on, if you just say you spread to 3 people, here 2 people, and each one of them spread to 2 people, you know, with only 2 steps, you've actually spread to 8 people who are in turn going to spread it to 2 people each, and et cetera, et cetera. So it grows very, very quickly because of this exponential behavior. So that's what I hope you understand about exponential functions. It's almost like it's a feedback loop. It's not a great word to use for it, but that's kind of how I think about it. The more you have, the more you grow, right? So that's what we want to take a look at. Welcome to 7.1, the first section in the Unit 5, which is the last unit that we cover in this class. So 7.1 is exponential functions and also their graphs. So like I said in the Unit 5 intro video, basically everything that we've looked at up to this point is kind of the same. It might not feel like it, but they mostly were. So here's the things that we were looking at. We looked at linear stuff, which was ax plus b. We looked at quadratic stuff, which was ax squared plus bx plus c. We also looked at like cubics. Now I never wrote the form of a cubic down, but that would be something cubed and then squared, you know, first power and constant. We also did some some rational expressions, but we never graphed them. I'm thinking about specifically graphing things. So these all may look very different, but they're not really. They do the same sorts of things. What they do is it's a variable raised to some power that you know, and then maybe also you multiply it by something and add a constant. But they're all basically like that. You take a variable, you raise it to a power, and that's basically your function and your graph. What we want to do in this section is kind of flip this on its head. So before it was variable to a known power, we're going to change it so it's a known power to a variable. So this is what's called an exponential function. So let's flip this. This gives us a new function type to explore. All right, so let's say an exponential function is a function of the form f of x, actually I'm going to write that on its own line so that it's really obvious. F of x is a to the x. And I'm going to have two conditions on f. So an exponential function is of this form where a is a parameter called the base. Okay. Okay, so what things are exponential functions? So 2 to the x, so this is an exponential function. 1/2 to the x would also be an exponential function. Let's do, I don't know, 1.79 to the x. All right, so all of these are exponential functions. So the base is the a, that constant. So in this case, 2 to the x, that's base 2. The second one is base 1/2. And the third one is base 1.79. All right. So I did have the condition. Actually, let me talk more about how this differs from the functions we were looking at before. So before we were looking at things like x squared, and now I'm using x squared and 2 to the x just because those are the smallest I could do. Also, everyone's fairly comfortable with x squared, and 2 to the x is pretty simple to graph. We're going to be graphing that here in a second. So before, x squared. So known power, unknown base, meaning the thing that I'm raising to a power. Actually, instead of saying known and unknown, we could say fixed power. The power is always the same and changing base. So then now when we're looking at 2 to the x, this is a changing power fixed base. So before, I would take various numbers, 2, -30, 1.5, and always square it, meaning thing times itself every time. What's different now is I'm only ever going to work with the number 2 or 3 or whatever my base is. I'm only ever going to work with that number 2, but I'm going to raise it to different powers. So 2 squared, 2 to the 5th, 2 to the 29th, 2 to the -3rd. So I'm going to be multiplying it a different number of times depending on what power I pick. So that's the difference between what we were doing and what we are going to do now. Okay, so I had a couple conditions. The conditions were that a couldn't be 1. So if a were 1, then no matter what power I picked, I got 1 out, meaning it's constant, right? So that's why I don't want a to be 1. A needs to be positive, so if A is negative, say -2, -3, then depending on the power, I either get something positive or negative. So it's what we call discontinuous, and you can't graph it nicely. So I don't want A to be negative for that reason. So that's the explanation behind my two conditions. This one, this is so it's not constant, and this one is so it's smooth. All right, the actual word would be continuous, but we don't need to worry about that actual definition.